Hello, I'm Amy and I'm part of Team 11 along with Jack, Nor, and Ibukan, and we'll be presenting our Capstone project for ISC on a prototype towbody for autonomous underwater vehicle docking.
As autonomous underwater vehicles are used for an increasing number and variety of missions, vehicle endurance inevitably becomes one of the key limitations of the vehicle, necessitating the vehicle to be recovered and the batteries either to be recharged or replaced. The recovery process can be time-consuming and dangerous, particularly in rough seas. One technique used to avoid this recovery process is to recharge the AUV while it remains submerged, as well as transfer data. While underwater docking stations are being developed for a variety of missions, in reality, in every instance the AUV is required to dock with a stationary docking system, either located on the sea bottom or hung from a stationary surface ship. However, there are numerous advantages to have the AUV dock with a mobile docking station, such as one that might be towed from a moving manned or unmanned surface vehicle. This project is intended to explore some of the challenges in designing an actively controlled towbody so that it can be used to dock with an AUV while remaining underwater.
So next I'll talk a bit about the project description. So we're actually the third Capstone team to work on the towbody. Our goal was to mainly focus on refining the control systems design and then design and implement a test program to be conducted at the Dalhousie Aquatron for validation. The purpose of the towbody prototype is to test if the towbody can correct its position, both pitch and roll, in the presence of a sea state or in any other external conditions, acting as a proof of concept for ISC. The hull of our prototype is shown along with the main external components labeled, all of which were implemented by previous teams. The towbody itself is also flooded. It has holes along the top and bottom to aid in this. Its internal components include linear actuators, potentiometers, and electronics, which we'll discuss in further detail later. As for how it's supposed to work, the towbody is instructed to change its depth, causing the actuators to move, which rotates the wings. The potentiometers are connected to the wings and they sense their angle. A control system then compares the pitch of the towbody to the angle of the wings and adjusts the angle of the wings until that error is zero and the towbody is at the instructed depth. The towbody is pulled by a cable that is attached to the bridle there, which simulates the body being towed by a vessel as discussed in the background. So testing was designed to take place at the Dalhousie Aquatron. This is basically a giant tank. It's 15 meters in diameter. It has a bridge that can rotate at various speeds, and it can also move up and down, so we have to be wary of this when designing a testing rig apparatus. But basically we used this space to collect data on how the towbody reacted as it was pulled along the perimeter of the tank. So the towbody must be able to be transported and lifted by two of the team members. Additionally, it is about 1 meter long and 1.5 feet wide, so it's well within the maximum dimensions. As the towbody is tested in the Aquatron, it of course must be remain operable at any of the possible depths, particularly the airfield enclosures, which are subjected to increased pressure at greater depths. Then the last two here are basically the purpose of our project. It should correct itself and restabilize after depth changes and also maintain its depth. Symmetric about any axis, and therefore we needed to be able to adjust the weight afterwards in order to have it horizontally trimmed. This is mainly so that during testing it wouldn't veer off and run into a wall. And then having the towbody about 1 pound positively buoyant would ensure that it would raise to the surface rather than floating to the bottom of the tank during testing, which would allow for easier retrieval of the towbody. And then lastly, the cables must be of sufficient length both for testing around the 15-meter diameter tank as well as for retrieval. As for safety, usability, and durability requirements, first, once the force on pulling the towbody stops, it takes a certain distance for the towbody to also stop. And again, to not have it run into any walls, this distance should ideally be kept to a minimum. Secondly, the topside tow just means the towbody will be pulled as is shown in the picture there. The bridle actually pivots on the towbody. And then lastly, the team was meant to conduct analyses analyzing adjustments on the control system.
The previous Capstone team had several designs on the Towbody that we left unchanged. These were the end caps, wings, body, bridle, wing shafts and bearings, and actuators. The reason these components were left unchanged was because they functioned as needed and there were no new requirements that involved these parts. The designs on the Towbody that our team did change were the electronics enclosure. The type of electronics enclosure that was used by the previous Capstone team had unfortunately leaked during testing and destroyed all the components. Therefore, all the components had to be replaced as well as the enclosure. The previous team believed that water entered the enclosure through gaps along the edges of the O-rings. Because we had to replace the electronics enclosure, we also had to replace the electronics enclosure mount. This was because the enclosure design dimensions changed and could no longer fit in the old mount. The potentiometer enclosure also had to be replaced along with all its components due to water leakage. Like the electronics enclosure, the potentiometer enclosure was also believed to have leaked through gaps along the edges of the O-rings. For this particular enclosure, the problem was more complex because the O-rings were wrapped around a rotating shaft. Therefore, it became more challenging to maintain an adequate seal for the watertight enclosure. Since the potentiometer enclosure's dimensions changed, the mount also had to be replaced. The mounting rig was redesigned as well. This was an unforeseen design change by our team because it only became necessary after we had selected a new potentiometer enclosure mount. Lastly, the code had to be refined.
So now that we've discussed the overview, here's a quick look at how it all fits together and what each of the components are responsible for, including the potentiometers, the actuators, and the electronics. So now we'll go into details about the individual components.
Modifications were made to the previous team's setup of the controller and control system. For the control system, PI control was adopted by removing the derivative term from the original PID code, as it is sensitive to noise. The original code focused on the depth change, in which the MPU's main concern was the pitch. The code was modified to add a zero roll condition maintaining 5-degree error in each direction. While feed-forward for reference tracking and state space representation were previously considered, these methods would only add more complexity to design in its early testing stages. Controller accessibility was later added as part of the team's requirement. Time control and surface control were considered as part of the design in order to instruct the tow body to change its depth within the aquatron tank. Originally, time control would involve having a predetermined instructions for the tow body, but that option was deemed to be flawed and it's inefficient. Surface control was then considered and selected as it allows for manual modification of depth during operation, allowing for more efficient testing and use of time.
So now a bit about the mechanical aspect of the electrical enclosure. We used a blue robotics enclosure to ensure that it remained watertight. We chose this over other options because it was pre-tested and has proven durability. As you can see on the picture on the right, the electronics are all still lit up after one of our tests. We also used underwater electrical connectors. You can see the bulkhead connectors on the left picture. This was also to ensure that the enclosure remained watertight, especially around the cables. Each one of these cables is connected to another one of the enclosures, so the motors or the potentiometer, and then one to surface control and power. And then you can also see, as for the components in the picture on the right, we used a 12-volt battery, an Arduino, and a motor controller inside the electrical enclosure.
Here we have the fully assembled potentiometer enclosure. It's filled with mineral oil. We have the tray here. It's made of PVC sheet. It's lying right in the center of the enclosure, which is made of acrylic plastic, and it rests in the center of the two flanges by the sides. We have both potentiometers sitting on it, and they're wired to the junction box, which is beneath the tray. And for the end caps, we have two end caps by the side. They're both made of acrylic plastic, and we have the potentiometer shafts connected with shaft couplings to extension shafts which come out of the end caps on both sides. And we also have timing pulleys which are screwed on to the extension shafts. And out of the end caps, we have a bulkhead electric connector and a vent on both sides. The electrical connector forms a watertight mate with a male connector and connects it to the electrical connector, while the vents create a vacuum in the enclosure to reduce the pressure to keep the end caps from popping out. For iteration 1, we had a base that would fit on the mounting rig and would require fasteners that would go through the side of the rig. And for iteration 2, we had a flat base and we have two covers that we would bolt down to the lower cylindrical holder to keep the potentiometer enclosure in place. For iteration 3, we added an extra leg to increase the stability, and we added gussets to increase the stiffness of the cylindrical holder. For the final design, we have a really simple design. We had this initial piece of plastic and we drilled a hole to fit the potentiometer enclosure in and created another hole on top to fit a set screw to keep the potentiometer enclosure in place. It's then bolted onto the mounting rig.
To meet our testing requirements, the team performed a buoyancy and trim test, a rotational test without the controls, and a rotational test with the controls. A translational test was going to be performed as well, but due to time constraints, this was not feasible. The purpose of building the towing rig was to help us perform the translational and rotational tests in the Aquatron. The design of the towing rig allows for a minimal tow angle, which helps maintain control of the tow body during tests. The reasoning behind this is the team believed that with a high tow angle, the tow body would constantly be pulled up to the surface of the water, which would disturb the motions we are trying to achieve. Another important part of this design is the towing rig can be used to perform both a translational and rotational test. The design is also versatile because it can be installed anywhere on the bridge's railings, which gave us a lot of flexibility. Most importantly, the towing rig was cheap to build, which was great because the team wanted to allocate most of its budget towards the tow body.
The first stage of testing involved a buoyancy and trim component. Buoyancy calculations were initially conducted to satisfy the positive buoyancy requirements prior to testing. The tow body's buoyancy and trim were visually inspected to confirm calculations. The stern of the tow body seemed to be slightly less buoyant than the bow due to the weight distribution from the internal components. This was quickly fixed by adding two 8-pound dive weights, one on each side of the electrical enclosure and the bow side, keeping the roll very minimal. This adjusted the weight distribution and allowed the bow to tip slightly forward while keeping the overall body positively buoyant. By tipping the bow forward, it allowed for the wing to stay in the water when being towed during the rotational test, which will be discussed in the next section.
The rotational test without controls was performed in a counterclockwise rotation using the Aquatron's bridge as shown in the picture. While performing this test, the tow body rolled slightly to the right, which was theoretically expected. Also during this test, our team changed the length of the tow cable to see how the tow body would respond. What we observed was the tow body move closer to the center of the Aquatron. This was the opposite of what we expected. Theoretically, as the cable length increases, we should have seen the tow body move closer to the wall of the Aquatron. What likely caused this was the inside wing being partially out of the water while the outer wing was fully submerged. Another possible cause is weight imbalance. The weight we added inside the tow body might have shifted while being towed or when we were applying it.
Due to the timing belt slip condition, potentiometer data was not reliable. This resulted in some last-minute changes to the code where the shaft angle data was no longer used. This change caused the PI control to be no longer feasible for the test as the feedback loop was no longer available. A simple alternative code was developed. As for the limited time provided for testing, the team was only able to perform a single test with the controls. This test focused on observing the vehicle dynamics underwater while having no roll component to be integrated into the code. This allowed the team to observe how much roll is generated in comparison with the body being on the surface, in order to compensate for it for future tests. As the tow body was towed by the bridge for a few minutes, data was recorded and stored into the microSD card. Depth was plotted against time, showing roughly where the tow body was hovering when fully submerged during the test. The tow body seemed to be rapidly submerging when released at the surface due to its negative buoyancy, which is expected. The first spike shows the point at which the tow cable experienced some tension, and that the tow body started getting pulled. The significant changes between the depth caused by the change of the tow cable length, as it was hard to tell at which depth the tow body was diving when it was observed by sight. The small variations in depth in the graph shows the attempt in the wings changing its angle of attack to adjust and reach the target depth as needed. These significant oscillations towards the end, at depth of below 1.5 meters, was caused by manually attempting to take the tow body out of the water and experiencing some difficulties, which caused the tow body to be submerged again very briefly after. By performing this test, it allowed for a better understanding of the vehicle dynamics and how to move forward. This allows for future considerations and further refinement of the control, as well as any buoyancy requirement changes.
Thank you for listening to our presentation, and now we'll be available to answer any questions.